In the winter of 1944, as the conflict stretched into its fifth exhausting year, Allied command began accelerating a new phase of the war, an engineering race against time. Factories in Britain and the United States were now operating at maximum strain, pushing the boundaries of materials, machining, and mass production. Archival reports from the period show that Allied leadership believed victory would be determined as much by industrial capability as by battlefield tactics. In this climate of urgency, a classified engineering program emerged, one that would reshape offensive strategy during the final year of the war. Although much of its documentation remains sealed for decades, surviving records indicate that its origins began in a converted foundry on the English coast. Inside that facility, dozens of engineers worked under blackout conditions, surrounded by blueprints pinned to wooden walls and tables stacked with precision-milled components. These were specialists from various fields: metallurgy, structural mechanics, aerodynamics, quietly reassigned from larger military projects. Workers later recalled the atmosphere as relentlessly focused, with long shifts that blurred into each other. The program was referred to only by its internal code, a series of letters and numbers never revealed in open correspondence. The breakthrough at the center of this story grew from a dire need. By early 1944, the Allies required a method to deliver heavier payloads with greater accuracy while maintaining acceleration in the air campaign. Traditional platforms were reaching their limits, and material fatigue was becoming a consistent operational threat. Engineers studied the failures of earlier designs, examining fracture lines, temperature warping, and structural inconsistencies caused by rapid cycling under combat conditions. Every discovery was cataloged, photographed, and fed back into the design pipeline. As German defenses adapted and strengthened, the Allied push for innovation intensified. Teams tested new alloys, experimented with reinforced weld patterns, and introduced machining techniques that were considered experimental for the time. These advances, though small individually, began converging into a cohesive system, one capable of altering the strategic balance. While the public knew nothing of the development underway, commanders at the highest levels monitored progress closely, aware that the outcome could influence the course of the war in its final phases.
By early spring, the engineering group had identified the core challenge: surviving the extreme stresses generated during high-altitude flight, combined with the demands of heavier payload integration. Previous models had exhibited buckling along critical load-bearing points, particularly where thinner skins met reinforced internal ribs. Engineers studying these failures realized that traditional alloy compositions were no longer adequate for the required performance. Archival workshop logs show that new metallurgical experiments began immediately, focusing on developing alloys with improved tensile strength and resistance to thermal expansion. One of the key insights came from an analysis of fractured components retrieved from downed aircraft. These parts showed distinctive patterns of microcracking, likely formed during rapid temperature changes at altitude. Metallurgists conducted controlled heating and cooling cycles, measuring deformation and searching for combinations that could withstand extreme gradients. Their findings led to the introduction of a revised alloy formula, incorporating carefully balanced trace elements, which improved both durability and weight distribution. Although still experimental, it offered a promising foundation for the project's most demanding structural requirements. Alongside material innovations, the design team refined the geometry of the internal framework. Engineers crafted wooden mock-ups, overlaying thin metal plates to test curvature, joint angles, and stress transfer paths. Every adjustment required recalculations performed by hand, slide rules clicking in dimly lit drafting rooms as the team tested assumptions. Archival reports suggest that these incremental changes drastically reduced stress concentrations at the design's weakest points. The most successful configurations were then machined into prototypes and subjected to vibration rigs that replicated wartime operational loads. Wind tunnel testing played an equally critical role. The project's aerodynamic specialists analyzed lift behavior, airflow stability, and turbulence patterns at various altitudes. Using smoke tracers and high-speed photography, they observed zones of instability and reshaped surfaces to better guide airflow. These refinements created a more stable and predictable platform, enabling greater accuracy for the system's intended payload. The cumulative effect of these breakthroughs signaled to Allied leadership that the project was nearing operational viability. What began as a theoretical investigation was now transforming into a functioning, highly advanced engineering system, poised to be tested under actual combat conditions before the year's end.
As development accelerated, workshop space became increasingly scarce. The engineering group relocated to a fortified hangar used previously for testing heavy transports. The structure's thick concrete walls and reinforced doors provided ideal security, shielding the classified project from aerial reconnaissance and unauthorized personnel. Inside, workers configured a dedicated assembly line capable of producing prototype components with unprecedented precision. Large milling machines hummed day and night, shaping metal parts to tolerances rarely achieved in wartime manufacturing. One of the project's most demanding tasks involved the integration of the new structural framework with improved aerodynamic surfaces. Engineers designed a series of interlocking components that could distribute impact forces evenly across the system. This design required craftsmanship that bordered on art. Sheet metal workers used English wheels, forming blocks, and rivet guns to shape and assemble parts with exceptional accuracy. Archival notes describe inspectors running their hands along curved surfaces, feeling for imperfections that could compromise performance. The team also addressed a critical engineering hurdle: vibration harmonics. At high speeds, even minor deviations in balance could produce oscillations powerful enough to fracture components. Using data gathered from previous Allied aircraft, engineers altered mass distribution, introduced stiffeners, and refined joint placement. Vibration benches inside the hangar hammered prototypes with controlled tremors, simulating the worst possible conditions. Only parts that passed these tests advanced to the next phase. Electrical specialists contributed to the breakthrough as well. Although WWII electronics were far simpler than modern systems, they still required careful shielding and robust insulation to survive altitude, moisture, and shock. Technicians wound copper coils, soldered contacts by hand, and tested circuits inside insulated chambers. Records indicate they focused on improving ignition reliability and signal stability, features essential for the system's accuracy. Despite the intense pace, security protocols remained strict. Workers signed daily logs, tools were counted every night, and communication outside the facility was heavily restricted. Even among the team, information was compartmentalized. Individuals knew only their section of the design. This secrecy gave rise to speculation,
though few fully understood the engineering ambition they were collectively constructing. By mid-1944, commanders overseeing the project believed the system could alter the strategic landscape. All that remained was rigorous field testing, conditions far more demanding than any laboratory or hangar could replicate.
Testing began at a remote airfield carved into the British countryside, where runways stretched across open fields and hedgerows acted as natural barriers. Archival flight logs show that the first prototype was transported under heavy canvas tarps, escorted by military police. Few personnel were permitted near it. Early morning mist shrouded the runway as engineers performed final checks, inspecting rivet lines, measuring torque values, and verifying that every structural element was aligned precisely to specification. Test procedures were methodical. Ground crews used portable fuel pumps, analog pressure gauges, and manual calibration tools to prepare the system. Nothing was automated. Every parameter was tracked by hand. As engines roared to life, technicians monitored vibration signatures and exhaust behavior, attuned to any irregularities that might signal structural stress. Observers documented the trial using large-format cameras fixed to tripods, capturing each stage from startup to shutdown. The first powered run produced valuable data. Engineers noted how the new alloy responded to heat buildup, how the aerodynamic surfaces behaved under accelerating airflow, and how the reinforced joints handled vibration. Several components required reinforcement, and adjustments were made immediately. The team worked through the night, filing down edges, rebalancing mounts, and applying revised rivet sequences. These modifications aligned the prototype more closely with the demands of high-altitude operations. Subsequent trials yielded incremental improvements. Reports describe smoother lift characteristics, steadier vibration patterns, and enhanced stability. Yet challenges persisted. A series of tests revealed unexpected stress concentrations near the inner support framework, forcing engineers to rethink load distribution. They introduced angled stiffeners and refined internal bracing, which significantly improved structural integrity. Archival diagrams from this period illustrate complex cross-sections, marked with inked calculations and annotations, a testament to the precision with which the team approached the work. As the prototype matured, Allied strategists monitored progress closely. Air commanders saw potential for a system capable of delivering heavier payloads deeper into enemy territory with unprecedented accuracy. Intelligence officers, aware of German technological advancements, emphasized the urgency of deployment. The combination of engineering innovation and strategic need transformed the project from a theoretical curiosity into a top priority wartime initiative.
By late summer 1944, momentum around the program intensified as the Allied advance across Western Europe accelerated. Field commanders requested more support for precision strikes against hardened German positions, and the engineering team understood the urgency. Inside the fortified hangar, crews assembled the second-generation prototype, an improved model incorporating dozens of refinements identified during earlier tests. Workers riveted reinforced internal ribs, installed strengthened joints, and fitted the newly balanced aerodynamic surfaces with meticulous attention. Every modification reflected thousands of hours of engineering labor, from alloy composition tweaks to revised structural reinforcements. Load testing procedures grew increasingly demanding. Engineers mounted the prototype onto reinforced stands, subjecting it to controlled force applications designed to simulate operational extremes. Mechanical presses generated immense pressure,
while analog dial gauges recorded minute changes in flexion. Technicians compared these readings against theoretical predictions, updating calculations to ensure the system met the stringent safety margins required for combat deployment. Archival reports describe engineers standing silently as the machine groaned under stress, listening for the slightest abnormal resonance that might signal a structural weakness. Parallel to structural advancements, aerodynamic experts continued refining surface behavior. Using wind tunnels, they introduced revised curvatures and edge transitions, improving stability in turbulent air. Smoke tracers revealed how airflow interacted with the design's contours, highlighting minor vortices that could disrupt accuracy at altitude. The team addressed these issues by adjusting panel angles and reinforcing key junctions. Each improvement was validated through repeated testing, ensuring that the system performed reliably under all expected weather conditions. The project's operational planners also intensified their assessments. They studied historical mission data, enemy troop movements, and industrial production capacities to determine how best to integrate the new system into the broader Allied strategy. Commanders believed it could enable a more targeted approach to disabling enemy resources, particularly rail nodes, supply depots, and fortified installations. Records indicate that discussions extended beyond engineering specifics, touching on logistics, deployment methods, and potential risks. But the system still faced a critical obstacle: performance reliability in variable flight conditions. Engineers recognized that atmospheric instability over continental Europe could magnify stress loads. To address this, they developed an enhanced internal bracing scheme that distributed forces more uniformly across the structure. This innovation reduced both vibration and fatigue, marking a significant milestone. With each breakthrough, anticipation grew. The Allies understood that a dependable, high-performance system could drastically influence the final phase of the war, accelerating the push into German territory while countering the evolving threats posed by enemy defenses. By the end of August 1944, preparations began for the most ambitious testing phase yet: full-capacity trials under conditions closely replicating frontline demands.
Full-capacity trials commenced at an isolated test range bordered by dense woodland and shielded from enemy observation. Archival maps indicate that the site had previously served as a training ground but was expanded to accommodate the program's scale. Engineers arrived before dawn, their breath visible in the cold morning air as they prepared the reinforced prototype for its most demanding evaluation. Every component, riveted seams, control linkages, internal stiffeners, underwent inspection using handheld lamps and magnifiers. The team understood that even a small imperfection could escalate under operational loads. The system was positioned on a dedicated launch platform supported by steel beams and concrete footings. Technicians connected analog instrumentation, pressure lines, mechanical sensors, vibration pickups, and manually calibrated dial meters. These devices offered real-time feedback during the trial, although limited by the technological constraints of the era. Photographers set up large-format cameras around the perimeter, ready to document each moment with the clarity necessary for later engineering analysis. When tests began, the prototype absorbed its first wave of full-capacity stress. The reinforced framework flexed under significant force, yet maintained structural coherence. Engineers observed the system's behavior closely, marking down vibration levels, heat dispersion patterns, and minor shifts in alignment. a controlled shock sequence designed to simulate combat conditions revealed areas needing further reinforcement. Notably, stress indicators along the inner support trusses displayed asymmetrical loading, prompting tactical redesigns to improve uniformity. Subsequent phases introduced more extreme conditions. The team increased pressure loads, accelerated vibration frequencies, and applied sustained force to replicate extended operational use. During one sequence, an unexpected resonance appeared, producing a noticeable tonal shift, an audible clue that experienced engineers immediately recognized. They halted the trial and traced the issue to a junction where two reinforced plates met at a slightly misaligned angle. This discovery underscored the importance of precision. A corrected fitting and revised rivet pattern resolved the instability. Meanwhile, aerodynamic specialists reviewed data from earlier test flights, correlating patterns of turbulence with structural performance. Their findings led to subtle surface modifications, such as adjusting panel curvature and refining fairing transitions. These enhancements improved airflow consistency and further stabilized the design at altitude. Archival notes stress that these changes, though small in appearance, significantly improved accuracy under real-world conditions. By the trial's conclusion, the prototype demonstrated marked improvement in resilience and stability. It completed the rigorous sequence without catastrophic failure, a milestone that convinced Allied strategists the system was nearing operational readiness. Still, final adjustments remained. Engineers prepared for the last phase, integrating the system into a frontline-capable configuration, ensuring it could endure the unforgiving realities of combat deployment in the final year of the war.
As autumn 1944 approached, the war in Europe entered a critical phase. The Allies pushed steadily eastward, but German defenses, though strained, remained formidable. Within this shifting landscape, the engineering project transitioned into its final integration stage. Archival memos show that high-level planners convened in secured briefing rooms to assess deployment feasibility, evaluating transport logistics, crew training requirements, and the potential strategic impact of the new system. Their discussions reflected the immense pressure to field innovations capable of accelerating the end of the conflict. Inside the fortified hangar, engineers adapted the prototype into its operational configuration. This phase required navigating the difficult balance between precision craftsmanship and mass production practicality. Workers refined assembly procedures, simplifying complex rivet sequences and standardizing component shapes to reduce manufacturing time. Machinists produced additional sets of reinforced internal trusses, ensuring consistent strength across all units. Detailed checklists guided each step, tracking torque values, alignment tolerances, and material inspections. Inspectors documented every component that passed through the line, stamping approvals using ink pads on clipped forms. Another critical challenge emerged: integrating the system with existing Allied aircraft platforms. Operational reports from bomber groups indicated varying structural capacities, vibration signatures, and aerodynamic characteristics. To address this, engineers constructed modular mounting hardware using high-strength alloys and reinforced steel plates. These mounts underwent rigorous load tests, confirming their ability to withstand altitude-induced stress and combat maneuvers. Once validated, crews installed the first operational unit onto a modified aircraft, securing it with hardened bolts and carefully calibrated couplings. Ground crews then rehearsed deployment procedures.
Without digital tools, the process relied entirely on analog instruments, pressure gauges, mechanical counters, and hand-timed sequences. Crew chiefs drilled their teams repeatedly, ensuring each step could be executed rapidly under wartime conditions. Archival witness accounts describe the intensity of these rehearsals. Crews working under lantern light, shouting over engine noise, and coordinating each action with the precision of a well-practiced machine. Meanwhile, intelligence officers monitored German technological efforts. Reports indicated that enemy engineers were attempting to reinforce industrial hubs and develop countermeasures against Allied air operations. This intelligence increased pressure to deploy the new system swiftly. Allied commanders believed that the engineering breakthrough could provide targeting advantages essential for disrupting enemy infrastructure during the winter campaign. By October 1944, the project neared its decisive moment. The first operational test under combat-like conditions was scheduled at a forward airfield closer to the Continental Front. Personnel prepared transport crates, secured components with packing straw, and loaded them onto trucks for guarded movement toward the front. Engineers, technicians, and flight crews followed by convoy, each aware that the system they had spent months refining was now poised for the ultimate test, proving its worth in an active war zone.
In November 1944, under low clouds and biting wind, the engineering team arrived at the forward airfield selected for the system's final proving trial. The site was rugged, muddy taxi lanes, temporary wooden huts, and aircraft parked beneath camouflage netting, but its proximity to the front made it ideal for assessing real operational challenges. Archival records show that security was tightened significantly. Armed sentries guarded the perimeter, access lists were checked hourly, and the prototype was concealed beneath tarpaulins whenever not undergoing preparation. Engineers began with exhaustive inspections, working shoulder to shoulder with ground crews. They examined every rivet line, tested the reinforced internal trusses for microfractures, and confirmed that the aerodynamic surfaces matched the most recent configuration diagrams. Mechanics calibrated the mounting hardware using torque wrenches and manual alignment gauges. Flight officers supervised fuel loading, verifying pressure values through analog dials while noting ambient temperature and humidity, variables that would affect high-altitude performance. As the modified aircraft taxied onto the runway for the trial mission, tension rippled through the assembled personnel. Large-format cameras documented the scene from elevated platforms, capturing exhaust plumes, tire compression, and wing flex as the aircraft accelerated. At liftoff, observers monitored vibration signatures transmitted through wired instrumentation. Initial data suggested strong structural cohesion. Heat distribution across the reinforced framework remained within safe margins, and vibration harmonics stayed stable even as the aircraft ascended into turbulent air. Over enemy-controlled territory, the new system faced its defining test. Records from post-mission reports described the aircraft encountering crosswinds and fluctuating air pressure, factors that historically caused accuracy deviations. Yet the reinforced design and refined aerodynamic contours performed as intended. Load-bearing components maintained alignment, airflow remained stable, and the system responded predictably to altitude adjustments. Archival intelligence summaries indicate the resulting strike achieved exceptional precision, disrupting critical infrastructure with far greater accuracy than earlier models had been capable of delivering. Upon return, crews conducted immediate post-flight evaluations. Engineers inspected the prototype for heat stress, joint fatigue, and deformation. To their surprise and relief, the structure showed minimal wear.
the reinforced alloy composition, revised rivet patterns, and optimized internal bracing had all contributed to remarkable resilience. Commanders at the airfield recognized the significance instantly. The breakthrough, once theoretical, had now proven itself in the unforgiving environment of active war. Within weeks, Allied planners began drafting large-scale integration strategies. Production orders were prepared, supply chains reorganized, and training programs expanded. Although wartime secrecy prevented any public acknowledgement, internal memos celebrated the achievement as one of the most impactful engineering successes of 1944. In the final months of the war, the system's deployment contributed to undermining enemy infrastructure at a critical moment, reinforcing the Allied advance. While many details remained classified for decades, surviving documents reveal that the program embodied the essence of wartime innovation, relentless experimentation, meticulous craftsmanship, and the unwavering belief that engineering could shape the course of history.